Okay, so the first thing we need to know is to have access to the data. And as I said, in exam, or I'll ask you to do some of these things. So if you don't know how to attach a data set, then it becomes a problem. If you don't need a data set, again, you can detach it. Okay, if you detach auto claims like this, let me start typing auto claims. So if I detach it, it should, okay, invalid name, let me see. We can, well, oh, sorry. That is to detach a package, sorry. Yeah, so it's the package that I need to detach, and then I won't have it. And auto claims is in it's in insurance, yeah, insurance data, yeah. So insurance data, a small I. Okay, like that. No, the name should. Okay, let me see. So detach object from the search path. So the name, the position, because we can use, I think maybe because it's a data, I can use RM, which is remove. So auto claims. Let's see. Yeah, okay. So this can be removed. That is removed, and there's no more there. Okay, but we should be able to use detach to detach a package. So let's see. And also attach. Yeah, so you detach package line. So why is it not working? So detach, let's say range, this should work. Okay, maybe I need to, okay. So usually there are changes in R and R Studio. So at first I just have to use detach by just calling the name. So now you need to actually specify whether it's a package, which means I'm sure it's been done in such a way that it will have multiple purpose. So the other, I think that would be too much, but because you can also, what is the easier way to teach this? Okay, so when you are doing simulation, we are here to, that's what I was going to do. So simulation means, okay, I have a real world, like what we did with the quanta plot. We had real data, right? I cannot be assessing anything I propose on a real data set. Okay, so for example, I've come out with a new estimator for a particular thing. I cannot just propose a new estimator, then I go and take real data set. So some of your project and thesis you'll be doing, you cannot say you have proposed a new estimator, and then your estimator, you just go and take insurance data from a company, and then you say I have estimated, let's say, the 99th quintile of the claims. Okay, we won't know whether that 99th quintile is actually correct or not. So you have to be in a world where you know exactly what has happened, and then you use what you are proposing to estimate what we know. So then you can check how well it approximates what is known. Okay, so that's what we call it a simulation, or you are simulating real life situation. That's it. Okay, now so sometimes you need to, there are what we call positions. So I have a global position that all my functions can get access to a data that is stored there. In some cases, I can also specify a position for them to take it from. So it's like, you have, let's say, array things, and then some are within others. But you can't have access to some when you are at the global level. But when you go in, you can get it. So you can use attach and detach for it, but it's mainly at a high level when you are doing serious level simulation. But maybe you'll get there very soon, so it's important we mention it. Okay, so now I want to use the claims data, I've detached it and so forth. So if I want it again, I must either use library of what? Reinsurance, or go to the package session and take it. Any one of them is the same, right? Okay, so reins like this, and then if I click library, so I can go here and check. You see, it's nothing. Okay, so whatever we've been doing is the same as doing library. You see, it's taken over there. Okay, so now I have library attached to my working environment. Okay, then I can now, let me just comment these ones out. So this is to remove an object. Remove an object. Okay. And this is to detach a package. I mean, virtually remove it. Not entirely from R, but from the working environment. Yeah. Okay. You can also remove a package if you don't want it in your R Studio altogether. Okay. All right, so now this is load reins in the working environment. Okay. All right. So now that we have insurance data, we can look at HIST, auto. We have it's auto claims, right? Auto claims. Oh, no, I haven't now attached it. So I must copy this and come down here and say data, that is now load the data, right? So that's, we load it into our working environment. So just after that, then I can now talk about auto claims. Usually don't type all together. Once you, why is it not coming? Okay, let me see, maybe. Oh, let's there were warnings. Okay, I must first check whether it is here. It's there, so why am I not getting it? Auto claims. Good, okay, now it's over. So what we were using was what? Paid, right? Paid, okay. So I can get a histogram of paid and look at how it behaves. Okay, so now look at this. You see, I say plot, and our studio is telling me that plot new, the margins too large. You see, I have, because I want you to see, I have enlarged the screen. Okay, now it wants to plot. The plot area is only this side, right? Yeah. And so it's too small for me to display the package, the data. So it won't come. You will see this error. So if you see this error, it means that your margin or the plotting area is quite small. You need to enlarge it. So I can come here and collapse the, what do we call it, the environment, so that all that place will now be for plotting. Okay, so I'll redo the plot, and now I can have it. Okay, so even that, it seems very, Oh, and it's because I have divided it into several parts as well. So you can use this brush to clear all of them. So every partition you have done will go with it. Then now I can go back and do it. Now I have my clean. So even this is not so good. First of all, I said those that don't come to class, I will see it through this. Okay, so if you no, okay, I can do that. Palma. See, I explained this. What did I say about this? The sides. Okay, yeah. Okay, and then I don't want to see the title, right? Histogram of auto. Nobody will know. They will ask you whether the claims are paid in dollars or something. Okay, so like that. So if I do this, it's not there. Also, S-Lab, I cannot be having histogram auto claims $sign paid. It doesn't. That's not a good label. So you need to change it to what? Paid. Or maybe to, if you are doing a presentation, just make it amount paid. You can even bring what is being paid, either in thousands or in dollars or in Ghana cedi, what have you. So maybe if it is in Ghana cedis, GAC, right, something like that. Okay, but that should be in quotation marks. We have it like this, so it becomes easier to present this, right? Okay, you can actually pop it out. Okay, like this. You can copy. If you right click, you can copy or save the image. Is that okay? So if you do your plotting now and you want to get it in your Word, you need to copy or save. I actually will save. When I save, then I can copy and paste it. Okay. When you are saving or copying, you should also be mindful that when you come to export, you save like this, right? So you see, if you have set your working directory, then it will go into your working directory straight away. So you give it a name. So this is what? Histogram paid, something like that, just to make sure. So if I go to my folder, my Act 602 2024, there it is, right? It will be saved over there. So here I can click on it, and then I see this plot. Then I can now copy and paste in Word. Is that okay? Yeah, and then I give figures so and so, and that's it. So that's how you get your plots saved. You go to export, you save as, you can save a PDF. You can also copy to your clipboard. So I can just copy like this, then it say copy plot. You can change the width and the height. So for example, if I want the height to be high, it was this, I can also say 200, right? And copy. So when I go to Word and I'm going to paste it, it will enlarge the height. So it's up to you to explore and see which one is okay. But essentially you should get a graph that, looks, maintains aspect ratio. Okay. In other words, you don't stretch it so much such that instead of a straight line, you have a constant graph. Okay. So we had paid. That's how you demonstrate this. You can get descriptive statistics and talk about it. You can get box plot and so forth. So we've done all those stuff. Okay. We can also use this. So what we did online, we wanted to check which of these distributions fit the data well, right? Oh, it's difficult to. I must start from the top to down. You remember this? So I'm just going to copy what is up there. I sent it to you to. I copy what is up there. So we are just repeating what we did online. Okay. So here, what do? I what I do is to split the plotting area into 3 parts. So 1 row, 3 columns, right? So it means I need to enlarge this. Other than that, let me just go 1 step back, zoom in, zoom. No, it should have been out. Yeah, okay, so I have a bit of space. Okay, so then I do the first exponential. So you plot the exponential plot. That doesn't look like a straight line. Then I do that of what? Pareto. We got this. So if you look at the exponential, it doesn't really explain these outliers well. The Pareto explains a bit of it, but the lower tail is not that better. Okay, the exponential does a better fit at the lower tail than the Pareto. Okay, then I check log normal, and that gives us more or less like a straight line. So in this case, we said the log normal seems a better distribution than what? The rest. Okay, what we are left with is now we need to now go and be able to estimate what are the parameters of these models. We haven't done that yet. We will do it later on. Okay, let's do one more. So please, in Auto BI, so I want you to do this on your own. So another example. In let me go to the package insurance, not reinsurance, so let me see if I can get one more distribution. There is log normal. Okay, so are you doing survival analysis too? So you know this. When you go to an interview, they will not ask you whether you did it as an elective. Nobody knows out there, they don't know whether you did an elective or not. So please let it there. But essentially, you should know what censoring is. Okay? So at this level, you should know. When we say a data set is censored, what do we mean? If a data set is censored, what about if it is truncated? Or that one too is an elective? Okay. Okay, but essentially whatever we have done, you see the reinsurance package also gives you, we can do all those things with also when the data is censored. In other words, you have a maximum value that above which you don't know anything about it. So for example, we are assessing people's survival to a particular disease. So we follow people for 10 years. After the 10 years, people will still be living, but so we don't know. We've got a study over there because of funding and other stuff. But we still want to leap into the years that the person will. Then we say we censored you at that point. So you can adapt whatever you are doing. If it is maximum likelihood, you can adapt the likelihood function to take into account the censoring. Okay, so these are things you should know. Sometimes too, you can censor what I'm saying, that you censor at the right, you can also censor at the left. Okay, and then we have what we call truncation. So sometimes people have experienced something before they even enroll on the program. Okay, so you can truncate them on the left truncated, right censored. So that's a research area, an active research area as well. Okay. Yes. Yes. Nobody. They said they have done it. But I have explained. You did not. Okay, so let's If we say we've been censored, okay, it means there's a cutoff. Okay, so let's say a study. You want to follow people and their evolution through when they acquire some disease. Okay, so let's say the study is for 2 years. It means I need to recruit people. Okay, now when I recruit people, I'll just follow them. Maybe you visit them. If it is, let's say, diabetes and hypertension, you go maybe every month to check their blood pressure, sugar level, and so forth. Within that 2 years. Within that 2 years, some will die, some will survive. Some will survive after the 2 years. Okay, but the statistics doesn't end there. The statistics, we still want to know how long they will live. Okay, so we censor them because we don't have the full data. So if you actually started at the beginning of the study, then it means you have survived for 2 years. We end 2 years, but you are still alive, so we cannot say you have died. So there will be a mark to show that you are still alive. Okay, but if your survival period is 1 year, you may have died. Some will also may join the study midway. So somebody will join it 1.5 years and then have a survival range of just 6 months. It doesn't mean you have died, right? Yeah, so that's how it is. Some will have 1 year, which means you have, if you have died, then you started at the beginning and then after the 1 year you died. Then we mark that you have died. So that's what we mean by a censored data. Okay. Then we can, but that, it means you have censored data on the right hand side, because like that. Good, okay. So when we are recruiting people to, we can say that we only recruit you if you have something like this. If the person doesn't have diabetes, what do you want the person to do in that study? So we can cut, it means that we are cutting people off, yeah, and you can term that as truncation. Yeah. Okay. All right. Okay. So an example, okay. So there's also auto BI. Okay, so let's look at you can even look at the head. The head of the data is that you want to see just some few rows, usually 6, right? And you can have tail as well, which is at the end of it. So the head of the data is like, so it will give you what data it is. I need to, so that's the head of, still. Okay, now I can see all of them at a go. Okay, so you can do the health fast, but essentially you have some auto insurance something. So the case number, the attorney, maybe the attorney that, and the claim. Okay, let's go to health file. Auto BI. So, usual. Why is it not? Okay, it doesn't come. But let's go to the health files. So this is the description. As I said, these are real data sets, right? Which you can use in your projects and theses that you are going to do. So this is data from what? Insurance Research Council, a division of the American Institute of Chartered Property Casualty Society, and so and so. The data was collected in 2002. Okay, so if you are doing your thesis and you want to use this, you can even go to the IRC's website and get more description of the data so that you add on to your preamble or the description of your data. Okay, then so how it was collected and so for the years and so forth, so you can get all of that. Okay, so if you look over here, it tells you that it was collected in 2008. It has demographic information on the claimant, the attorney involvement, economic loss in thousands, among other variables. We consider here a sample of N is equal to 1,340 losses from a single state. So the full tool study contains over 70,000. Okay, so that's what I'm saying. So if you want to use this data, then you now track back to the IRC website. If it is not there, you can send an email, or sometimes they bank it in the data a bank that you can have access to it. So that's is the real data set that you can use for a study. Is that okay? Okay, good. All right. So now, what I want you to do is that I want you to describe the laws. Is that okay? All right. Now, so that's our exercise. Yes. Describe the laws data for this company. Then, when you are done, we want to check whether the laws for those who have seat belt, they say whether or not claimant was wearing seat belt, stroke child restraint. 1, if yes. 2, if no. 3, if not applicable. So it means that the losses, we can check whether they are the sizes are different for this group. Is that okay? Please, you remember we did something like this. Okay. So you have a data set. Oh, I did not bring marker. Do you have a marker here? Okay. So please, first of all, you do the descriptive statistics for laws on your own. When you are done, thank you. When you are done, we will want to check whether the losses are different per that seatbelt. What I'm saying is that the data can also be grouped into 3. Those who were wearing seatbelt, those who were not, and those that are not applicable. So it means that maybe here the first person loss is 1,000, then 2,000, then 1,005, and so forth. They may not be the same. The sizes may be different, right? Then you come here, maybe 2,000. So we can actually check which one has the highest, or in terms of averages, which one costs more. Okay, the first thing I want you to do is that you have this loss data. How would you describe it? Yes. What can you do to describe this data? You don't understand? Okay, so you have loss data in front of you. If you go to Auto BI, it says loss, isn't it? Claimant's total economic loss, and it's a vector. So we want you to describe this data. If you were to do some work on this, and we want you to describe descriptive statistics, I mean, how are you going to do it? What kind of statistics will you use? And then now you can now go to R and present it. That's what I mean. First of all, what kind of data is this? It is what? Good. Okay. So if you have a quantitative data and you want to describe it, let's say a new, you want to woo an investor to invest in the insurance company, and you say these are the losses that are coming. How are you going to describe this data to the person? That's what I'm asking you. Yes. So one, you can use a histogram. Okay. So please do. What else? You can use what? Scatter plot. Okay. Why are you using bar graph? Okay, you say histogram and then bar. Now somebody says bar graph. Which one should we go with? Why? The data is what? I heard something. Continuous. Well, okay, but this is a quantitative data. You know, they are values, that amount of money. Yeah, so we only use the bar graphs for qualitative. Yeah, so this you have to use maybe a histogram. What else can we use? What else can we use? What other plot apart from histogram can you use? What? Scatter plot. I was going to ask, how are you going to do the scatter plot? This is one vector. When you are doing scatter plot, you need to. You can actually plot it, but you must tell me what the scatter plot will look like. So mostly when you are doing when you get the data you want to analyze it, I mean, it's those basic statistics you did at the undergraduate level. Okay, so please don't forget this. So we can use a histogram. That's good. What other plots? We talked about box plots. Good. You've forgotten box plots. You can even use a stem and leaf as well. Okay, we did all that. Okay, so please do your histogram. How are you going to do it? Somebody should tell me how we should do it. You load the data. Okay, good. Okay. So we need to do data what? Auto BI. Auto B. Okay, then we run it. Okay, what next? So here we talk about descriptive statistics. For loss data, descriptive statistics for loss data, loss data in auto BI. Okay. So you said histogram. How do I get a histogram? Hist. Okay, good. Okay, then what do I have to do? What? Auto BI. Dollar sign. Loss. Good. What else? That's all. Okay. Man. Nothing. Okay. So let's try this and then we can. So it looks like this. Why am I getting it like that? I have divided a plot, so I need to take it off, right? Okay. One way to take it off is that you can also say per, then the margin I just do, is it no? This is not margin. MF, yeah, MF rule. So what should it be? 1, good. Only 1 and 1. Rows and columns, yeah. Okay, so it should be 1. Okay, now we have it like this. So we can now go in and modify it. So what do we have to do now? The loss has that dollar sign. It's not good, so we need to what? Take it off. How do we take it off? Or modify it? S-lab, good. And then we do this. We can now go to the health files and see what? The claimant's loss, total economic loss in thousands. Right? So whatever data we are getting over there is like it's been divided by 1,000. So to get the actual one, we have to multiply it by 1,000. Okay, so we can just use this total economic loss. So I copy and then I paste it over there. Total economic loss. Okay, then I do it again like that. So if you are doing a presentation, or even if it is in your report, as soon as the reader sees this, you know what this histogram is about. So labeling in a histogram is very good. So the frequency, if you like, you can also look at the number of claimants. That's what the frequency is. The number of people who claimed this amount. Okay, so you have a histogram like this. How are you going to describe this? That's also very important. So in your work, we allocate marks for the programming, allocate marks for your interpretation. Because if you have the graph and you can interpret, Who should do it for you? So they say you are the actor, and then you do your plot, you bring it to the one from marketing department. What is the person going to do? So you must you must interpret it. So what can we say about this? So that's very important. Please make sure that the basic statistics. Yes. What? Most of the losses are 200,000. Okay, good. You remember I said you can even do percentages. You can use the percent, so you can check how many are even after 1,000. And no, this is 100,000, right? Because everything is in thousands. So 100,000, how many are over 100,000? How many are over 200,000 and so forth. But we'll come to that. When we fit distributions, I said you'll be doing this. So you will be checking probabilities that it is greater than this. But that's important for reinsurance. If the thing is rare and it doesn't happen so much, if you are doing reinsurance, you will now decide whether to go in or not. And you are the person who advised. So you must know this. Okay. So let's move on. What other thing can we use? What other graph or descriptive statistics? We can use the box plot. So let's look at the box plot. Okay. So you have to be doing this. So please make sure nobody will do it for you. Okay. And I mean, I will not tell you that if I give you a question, I will not tell you that plot a histogram. Because I will say describe. It's up to you to, explore. When you are at the workplace, when your boss gives you, they will not tell you that go and use it. So, but at the end of the day, they want to see something. Exactly. So let's look at it like that. Okay, so if you look at this, it's the same as the histogram. You have outliers which are so huge. Okay, there were some claims that were so huge, so they are making everything look like there's nothing over there. But there is. Okay, all right. So that's it with the plot. We can use the stem and leaf as well. Okay, stem, auto BI loss as well. Okay, so remember the stem and leaf gives you, but what's the advantage of the stem and leaf over the histogram? Who can tell us? So you see, I have to be going on to use. So this is 100. Okay, so even the 200, there were only two. Only two values were beyond two. Oh no, there's another one. So in the 200,000 column, only two values. Then it goes up to what? Over, in this case, 1 million, right? Yeah. There was one which was what? That means it will be 107. So almost 1 million and what? Is it 700,000? Yeah, that value. Okay, so we will do this. So all the 600,000, there was no claim. 300,000, there was no claim within that interval. From 300 to 900,000, there was no claim like that. Okay, so those claims that you were getting from 100,000 onwards, even most of them were what? Below 100,000. Okay, so these are now the 100,000. These are all being treated as what? Outliers, and that's what you see in the box plot over there. And the histogram, you see that all of them are here, but the length extends to this place. So those values were what we were seeing over there. Okay. You can also go and check look over here. Look at the data. Okay. So if we scroll down, we'll see the number. So over 1,000. If you have over 1,340, there are 1,340 claimants, and only one was over 1 million. Only 3 were beyond what, 200,000. Then the bars will be very small compared to those over 100. So that's what you are seeing over there. Okay, and of course, remember that we did describe, right? So you can go and get your. So all this nobody will tell you, but from your, you should be able to know that. Okay, so we can describe. So remember, describe is in psych. So if you don't upload psych, you won't have anything like that. Okay, so we can now see descriptive statistics on this. Okay, so number of observations 1340, just like I indicated. The mean is what? 5.95, which means it will be what? We have to multiply this by 1,000, right? In reality, that's the 5.95 thousand, okay, which is almost 600. Okay. The standard deviation is 33.1 thousand, okay? Because standard deviation will be in the same unit as the values that you are dealing with. The median is 2.33. Who can explain to us why the median is smaller than the mean? Yes, the median is 2.33 thousand. The mean is 5.95 thousand. Who can explain to us why this is so? Is it left skewed? It's right skewed. Okay. So what is it? Is it why is it shifting to the right? Okay. So why is the mean greater than the median? Yes. Yeah. When you are computing the mean, it sums them. So if you have the very large one, that 1 point something million will shift the mean towards itself, right? Okay, so that's why the mean is now greater than what? The median. Is everybody okay with this? Okay, good. Okay, so I mean, these are to help you describe your data. Okay, so when you are doing your thesis and you have a real data set, you start from descriptive statistics. Get the data, plot it. Let's see what the data is. Get some peculiar statistics on it, report on it. That will form one section of your project before you move on to do any model fitting and so forth. So this is very important. Okay. So the skewness, you said it is skewed to, so is it positive or negatively skewed? Positive. So look at the skewness, it's 25, quite large. What is the skewness of a normal distribution? Yeah, 0. Yeah, so the skewness is 0. So if you have 25, that is, and you see it in the graph that it's almost one side, and that is. The kurtosis is also large. What else? The maximum, you see the maximum, it was 107. If you get to the stem and leaf, okay, so there was an approximation. The actual value is 1067. So it approximated 10 and then 67, so it rounds it up to 7. But the beauty with the stem and leaf is that we can retrieve all the observation back. But if I give you a histogram and you don't know the real data, you can't tell me what they are. All you know is that within this range, this is the number of people. But you cannot tell us the actual losses. But in the stem and leaf, we can actually see, even though it's approximation, but you can see actually what is it. So when I was here, I was able to say that the largest value is 101 million and 700,000. Something like that. Okay. All right. What else? No, 70,000, right? 70,000. Yeah, 1,070,000. If it's 1.7, the 7 should have been at the other side. Okay. What else can we talk about? Okay, so that's how you do descriptive statistics. Is everybody okay with this? Okay, good. Then let's come here. Now, if we look at the data, let's go back to how the data looks like. Okay, so you see there is loss. Oh, this one is. Are we dealing with the auto BI? Or this? Okay, the loss is down there, so I couldn't see it. So there is loss. Now, if you come to the seed belt, you see that is category. So the first person is in category 1, and the loss was 3.34.94. Is that okay? Okay, when we go to the fourth person, that fourth person is in the seed belt category 2. And if you go to the help, you will see what that 2 is. What was the 2? I think no, not wearing or something. So 2 is what? No, yeah. So equal to 2 if no. So whether or not the claimant was wearing, so those that were not wearing seatbelt. So from this data, we can infer when we do our descriptives on this to see whether those that were not wearing seatbelt data, their losses were more. Okay, that will help you to, if let's say you want the habit of people to insure them. So for example, the UK, you need to fill online form. Okay, the insurance is not tied to the car. The car is also part, but the driver is also part. But in our jurisdiction, we only insure the car, so that if the driver has a license, you can just hop in. If there's an accident, the insurance company comes in. Okay, here they will just link you to the car, so you cannot. Maybe there will be a general one, but you cannot insure it, and then I'll go and drive, and then when something happens, the insurance company can, because they say if you change it, you go and then get a new insurance, and so forth. So some jurisdictions are like that. Ours is a general one. Okay, so if let's say you ask questions and the person says that I do not like wearing seatbelt, then if, assuming we haven't done the statistics, but if the statistics shows that if you are not wearing seatbelt and there's an accident, the loss is more, then such a person will pay more premium than the person who says that I always wear my seatbelt as soon as I enter the car. So that's the sort of thing we want to do. Okay, so let's see. How should we do that? How should we do that? We have the data, okay? We have I can do it again. That's the head of the data. You have the data is in this form, right? You have the loss. You have the seatbelt data as well, the corresponding. How can we get either a graph or do some descriptive statistics that will be tied to the seatbelt? Okay. The bar chart. So which one will be your response variable?
So the seatbelt will be X. The loss will be the Y.
Is that how you do bar chart? The seatbelt is categorical. Good. But what about your bar chart? You think of it, your bar chart, the bar is what? The bar, what is the bar? Is a free, good, okay. So you ask yourself, if you say seatbelt and you have a loss, is the loss a frequency? No. Yeah, so you have to be very careful when you are otherwise you mess up. And you see, if you take part in, let's say, even PhD vivas and so from the other department, okay, when we go, you have to keep quiet. Other than that, you you let somebody else. So you just look at it, because what you are saying, somebody can plot it. And for a statistician, when you see it, I mean, if you say it, it means the whole work needs to be pulled down. And so it's better that maybe you go to the bank. You don't want to be the, what is it, the Judas in the room. But it's interesting when you go, you see the way people are, abusing statistics. Okay, so when you have something like that, you remember ANOVA, analysis of variance. This is an example of an analysis of variance problem. But remember that this is claims, so analysis of variance will say, well, each of the distributions should be from a normal distribution. Does the data looks like a normal distribution? Absolutely no. So what do? If we still want to go along the lines of checking whether our averages are the same for each group, non-parametric statistics, right? Okay, so you can, for example, use the Kruskal-Wallis test. Okay, so please, those basic test of hypothesis, and you should be very familiar with them. So take time and revise. As for here, I'll ask you, even though it is not on those things, because you can't just, it's not just a program, and you should make sense out of it. Okay, so let's see. The first one, so descriptives, we said we want to what? We want to describe the losses per seat belt. A seat belt what? Seat belt usage, right? Something like that. Okay. So the first one is like box plot is good. So this is what you do. First of, remember, maybe I should go back to the help files for box plot. I talked about this when we did it, but let me go back so that just people will. Okay, so the box plot, you see this. I said that you need only this. Okay, so I have the data, I have a formula. What formula do I want? I want the loss data as a function of what? The seat belt usage. So that I will get plots for only seat belt, those who use seat belt, those who do not, and the three. Is that okay? Yeah, so that's what we're going to do. So you copy up to the data, and you paste over here. Okay. Then the data is not null. What data are we looking at? What data are we looking at? Auto BI. Okay. What is our response? What do we want to plot? And how do we want to categorize it? So what you want to plot is your response variable. It's like you are doing Y on X, but the X is categorical, as you said. But we can't use bar because of frequency. It's actually several losses. Yeah. Okay. So what we want to do is that I need to go here and check the loss. The loss data is spelled. You have to spell it correctly, otherwise it will not. Because I have the data, so I'm only using the variables to plot. So loss is like this. And then you use tilde. So that is a formula, Y on X. So tilde, that should be on the extreme left, top left of your keyboard. Tilde, top left on your keyboard. You see it over there. Then what is our X? Our X is what? Seat belt, like this. So this is what we want to do. So we plot it like this. Okay. So what does this tell us? There was no 3. Remember, 3 was what? Not applicable. Yes. And in the data that we were given, there's no 3. So you see you have only two boxes. Now, if you look at this, one is that they were what? They were wearing seatbelts. Good. And 2, not wearing. Okay. What can you say about the losses according to these 2? Can we really say that? It's a bit dicey. You see, that most of the observations are down here, but you can hardly see any difference. But there are some outliers. Good. Okay, so this one has very huge outliers. So yes, you may say that, but we cannot do this until we do a test of hypothesis. Is that okay? Yeah, to rule out this. Okay. So, but this is how you compare data sets. Okay, let's see whether we'll get some other. What were some of the other categorical variables in this? Oh, we can check even males, claim sex, and we can check. Let's use marital. Maybe that will get some interesting. Maybe those who are married, they are more careful. Maybe. We are yet to see. They may be even careless than. Okay. Okay. So, but please, do you understand what is going on? Yeah, so this one we are going to get, you see, so we have all this. That were 4. And you can go back and check what 1 is. 1 is if married. 2 is what? If single. 3 is widowed. And 4 is what? Divorced or separated. So let's see. Oh, but those, therefore, those who are married were they were incurring more loss. That's why it's America, not here. Okay, so that's how when you have a data set, they will just give you the data. That is the data concerning our customers. But as a data scientist or statistician or actuary, you play around with it. And then you can get some interesting results and report on it. Okay, so all these will help you in your premium calculations. So it's not just your life contingencies alone that you put it in a formula and then you get this. But you can put in some of this, auxiliary information to help you strategize and so forth. Okay. All right. So let's see. Now, let me branch a bit into hypothesis testing before we get back to where we wanted to get to. So is everybody following the story? Yes. We have losses. Now we're able to check whether the losses, the categories within the customers are affecting the losses. We look at marital status. It's like we can't tell with certainty, but with this one we are describing. Okay, so we say that those who are married tend towards. There's a likelihood that they will incur more losses. Right? Yes, there are very large losses over there. Okay, so if you look at those who are divorced and separated, an outlier over there is not an outlier in what? The married people. Is that okay? So that's how your stories will be. So then in a meeting, then you say, well, then those who are separated, so if somebody is married, then the next time the person is coming to renew, the person is separated. Then if you want to retain the customer, you may reduce the what? The premium. Because you know that this is what the data is telling you. and so forth. So that's it. Okay. Now, but we should be able to tell with certainty whether what we are seeing and describing actually statistically it is significant. So we may see it like this, but there will be no difference between them. Okay. Now the question is, can we go back to this one? This, we have only two groups. Those who wear seatbelt and those who do not. Okay. Now, what else can we use to check whether the averages are the same? T. Which of the T's? Two tails. You are missing the terms together. Boxing all of them. Okay, so t-test, but there are three types of t-test. We can have a single one, and we can have two samples. The two samples, we can have independent and we can have dependent. So you need to specify. So this one we have two different groups, so we rule out the one. Okay. The next thing is, are these independent or dependent? If they are dependent, I expect that the measurement will be, or the data should be on the same person. So the unit you are taking the measurements on should be the same, and there should be before and after measurement. Okay. So for example, those wearing seat belts, are they the same people who are not wearing seat belts? So we say that this will not be paired or dependent. Is that okay? They are independent. You cannot be wearing seat belt and not wearing seat belt at the same time. Is that okay? So that's how you analyze to come out with a proper test. Okay. So we want to test whether wearing seat belt reduces your accident losses. So this can be something that, if you are the insurance company, you want to, Is that okay? Now, then we need to set a hypothesis and test it, right? Okay. We see that they are independent. So if we want to, how do you test hypothesis? Okay, so one, we need a null and what? Alternative hypothesis. What else? Two. We need test statistics, right? Three. What else? We need some critical region. Critical region for your test. Okay, once we have that, we can then make a decision. And then 5, we conclude. Okay, so here, our null hypothesis and alternative hypothesis will be like this. We have some mu 1 minus mu 2 should be equal to 0. So this is wearing seatbelt, not wearing seatbelt. Okay. You see how I framed the question? I said we want to find out whether wearing seatbelt leads to what? That's what intuitively you would say. That if you wear seatbelt, you expect that when there is an accident, if it is injury, that's what they say. So it means that this is a mean of wearing seatbelt, right? So if I subtract that of those who were not wearing seatbelt, what will happen? I should get no. I want to derive the alternative hypothesis. We want to find, that's what they say, that if you wear seatbelt you are protected when there's an accident. So I expect that if somebody is not wearing seat belt, when there's an accident, the injury and so forth will be more. If it is more, there will be more losses, isn't it? So we want to test this hypothesis. And I have stated that the null hypothesis will be that there's no difference within the losses. The alternative will be that there's a difference. Now you need to tell this is not two-tailed, right? That's what we mean by a two-tailed or one-tailed. This should be a one-tailed test. But the one-tailed, it can be less than 0 or greater than 0. But we need to find, that's why we are we are deducing from it. Now, if this is the average from those who were wearing seatbelt, and this is that they are not wearing seatbelt, then a 5 from the preamble we've been given, mu1 minus mu2 should be what? Not equal to 0 means it can be greater than 0 or less than 0. But the claim is that if you are wearing seatbelt, your loss will be smaller. So what will be your null hypothesis? Mu1 minus mu2. Mu1 minus mu2 should be less than 0. If it is less than 0, what does it mean? Mu1 is less than mu2. Okay, so that's a claim. Okay, so if we reject this hypothesis, then it means whatever is being claimed is true. Is that okay? All right. Okay. The next thing we need to do is that these t-tests assume normality. But if you look at this, it's not normal. None of them is from a normal distribution. Is that okay? So yes, we need to get a counterpart of these t-tests. You remember in your undergraduate we talk about sign test, right? Wilcoxon. So in R we can use the Wilcoxon sign test. Is that okay? So that's what you do. Then, I mean, at your level you should know that, okay, this is not normal, so we use a non-parametric sign test. Okay, then you go around it. But if we were going to use the t, then we have the t is what? S bar minus mu divided by what? Do we know? We don't know the population, so we do this, right? Okay. But remember that in this case, the sample size is very big, 1,003. So if I divide them into 2, if you look at what is over there, each of them will be at least greater than 30. So this is not different from the normal test we do. That's it. Okay, but the t will be like that. Then we say that if this is true, if there's no difference between them, then they should have a t with what? N1 plus N2 minus 2 degrees of freedom. So that's the distribution of the test statistics. Okay. Then we can then get our critical region. If we look at our critical region, it means that we'll reject for what? Smaller values. What is smaller values? So we'll have something like this. Okay. And we have our t alpha on 2, n1 plus n2 minus 2 here. Anything over here we reject. If it is over here, we do not reject. And so forth. Of course, 0 will be here. So when we read it from tables, we can negate it. So that's it. That's your critical region. Then we make a decision. How can we make a decision? We go to our data, we compute this. Maybe t gives us a value 9. Okay, so we now have to make a decision. You come here, because this is negative, t is equal to 9 will be where? So what do? You fail to reject. If you fail to reject, it means that wearing seatbelt does not lead to what? A reduction in losses. Either it is equal or it may even be what? Greater. Is everybody okay with it? Okay, good. So that's it. And then we conclude. Our conclusion is that wearing of seatbelt does not necessarily lead to what? A reduction in the losses. If we go to the other one, the next one that we did, that one is more than 2, right? So you can't be using the t. This is the ANOVA test. So you ask yourself, is this normally this? All this you can test it in now, right? You can test the using Shapiro test or the Bartlett test as well. Yeah, and then you have to also check whether it has constant variance, and so remember your ANOVA assumptions. So at this time you can implement all those things to do it. So let's first look at this. So first of all, I can check. You know the Shapiro test. Okay. So this is normality, as you can see. Okay. So you can test for normality because you want to check whether you should use a t-test, right? So check for normality. Normality. And that you use a Shapiro-Wilk test. Okay. There are other tests like the Dannett and so forth. Also Shapiro. And as I said, anything you want to do, if you don't, you just go to Google and check. How do you do this in R? You'll get. So Shapiro, perform or Shapiro-Wilk test of normality. Okay. Now, so X is what? Just a numeric vector. Okay. So remember that if, from probability distribution, if I have a normal distribution and I divide them into different categories, I expect to have the same normal. Okay, I can add normal random variables, I get a normal random variable and so forth. Okay. So what am I saying? That we can actually test only the auto BI. But if you like, you can also test it based on the groups. Okay. So we can test this and see. So somebody mentioned p-values. So that's it. So this is the Shapiro-Wilk test. Okay, you get this. So test. The data is this. This is the test statistics. It's called W, the Wilk test. And the p-value is almost close to what? Close to 0, right? Okay. So in this case, what do? We will reject the null hypothesis. I did not say this. There are 3 ways to conduct a test of hypothesis. What we did is one way. The other way is to use a p-value. So, but in your p-value, you still need your test statistics. What is a p-value? What is a p-value in the test of hypothesis? Please, you have to know this from basic principles, okay? Okay, so you see, please pay attention. The p-value, if I want to compute it, will be the probability that I record a value more extreme than what the sample is giving me. Okay? So, in basic form, but the more extreme is relative to what you are doing. Okay. So here, you see we were only dealing with left tail, right? So if I get something in the left tail, then it is more extreme than what the sample has now. Is everybody okay with it? Oh. Okay. You got 9. Did you reject the null hypothesis? So that's not extreme. Okay? It coincides with the status quo. So when I say more extreme, I mean deviation from the status quo. Is that okay? So the probability of recording a sample more extreme than what we have now is the p-value. Is that okay? Okay. So when we got this, if we compute the probability, okay, of this, okay, it will not be more. In other words, it will be more than, okay, it will be more in the sense that it doesn't go against this. Remember, you only reject the null hypothesis if the p-value is quite small. In other words, you do not have enough evidence to what? to back this one. Okay, so that's it. So more extreme here means that we will record the sample that will give us a T in this region. Okay. If I have two tails, then more extreme means smaller and also larger. So in your undergraduate, when you were computing such a p-value, you find what is here and then you multiply it by 2. That's it. Okay, so the more extreme in two sample cases, you have very large observations and very small observations. If it is in the right tail, so if we were to do that one, then we are going to have this that we reject over here. So what is more extreme in this case? That is values greater than this one. That's it. So if you look at this from this way, you should be able to explain what we mean by a p-value. Okay. So this one, we reject the null hypothesis. So in the Shapiro test, it tells us that H0 is that the data is normal. Okay, so this, close to 0, we reject it outright. It is not normal. Okay, so because it's not normal, so I'll just make a comment and say that, so since the p-value okay, let me just copy the value. So since p-value is less than we reject all normality. So the data is not normal. Okay. Then I'm going to comment that since normality assumption is, I'll make this available to you. So since the normality assumption is violated, we cannot use t-test, but rather a non-parametric version. And in this case, that is Will-Cousins test. Okay, so that is a simple note on this. Okay. These are Will-Cousins sign, rank test, and so forth. It's in basic statistics. Okay. So now let's go and look for, if it was t-test, we use t.test. Let me just do the help files for both and show you. So if it is t-test, you use t.test. So if you don't know, you say, how do you conduct t-test in R? You will see this in no. You just check. That is at the workplace. Well, okay, so at first, I did not mind, but, they enjoy it. Oh, but I know how to set it so that it will be apart. But now that there's ChatGPT and so forth. But actually, people were sending the questions to people outside to do it, and a whole lot. So we just UGCS, we've seen it. So now they will just restrict. You can only take it at this place. At first you are there, even undergraduate. The person just opens it, and somebody is somewhere writing the test for the person. You say, hey, you'll be there. Exams in this university. People do magic. Okay, so let's see. But we've realized that the t-test is not appropriate in this case. Okay, so but if you want to do a t-test, a student t-test, It performs 1 and 2 sample t-tests. I've explained this, right? Okay. So this is how it looks like. So your X will be the first data, your Y the second data. Okay. Then the alternative. Remember, we have what? Greater than, then I can get 1 like this. The alternative, you can have 3 of them. The first one will be not equal to 0. And then we can have mu1 minus mu2 greater than 0, or mu1 minus what? mu2 less than 0. So these are the 3 possible hypotheses you can test. So the two-sided is this one. It's okay. Is it okay? Then you have less. Less will be that one. Okay? And then greater will be that one. So depending on what you want to test, you will go with one of them. Okay? By default, it will test for two-sided. So if you don't provide any alternative hypothesis, it will take it as a two-sided test. But remember, if it is one-sided, like the seatbelt example, and you choose two-sided, your test is wrong. Is that okay? All right, okay. Then mu is 0. So by default, you see mu1 minus mu2 is 0. But it is not always the case. Because I may also ask you to check whether wearing seatbelt, those wearing seatbelt, their average loss is, let's say, 20,000 less than those who do not wear seatbelt. Is everybody okay with this? The difference between them, we can also check whether it is greater than or equal to a particular value. So when that is the case, for example, if I ask you to check whether this is 50, then this one would have been 50. This will be 50. This will be 50. Is that okay? Yeah. So in that case, mu is not 50. Mu is not 0, but we'll replace it with what? 50. So that's it. Then remember that the t-test, we say we have independent and what? Dependent or paired. So this paired by default is false, which means it tests for independence if you don't specify paired. Is everybody okay with it? Yeah, so if, let's say, you remember the anorexia data, that one, they measure their weight before and then their weight after the program. So that is a paired test. So if we were to check whether there is a substantial increase in their weight, that will be a paired test. So we change the false to what? True. Okay. And then variance, well, if you want to do test this. For example, this one, let's go there. You need to check whether the variances are the same. Okay? If they are the same, there's one, do you remember this? Pooled variance in undergraduate. This one. S squared, N1 minus 1, S1 squared plus N2 minus 1, S2 squared divided by what? N1 plus N2 minus 2. Okay. Hey, I'm not going to ask you to do this. Okay, but here, what does this mean? If the variances are close together, okay, they don't differ from themselves statistically, then we can pull them together. But if they are so different, then you just leave them in the formula like this. T is equal to x bar 1 minus x bar 2 minus mu 1 minus mu 2 divided by the standard error of that one, which is, you remember this one, mu 1 squared n1 plus what? Mu 2 squared n2. If they are the same, then this is equal to that, and then I can pull it out. That's what we mean by pool variance. So that's it. So we also need to check that. So if they are the same, what do? You can now say that var dot equal is all true. If they are not, it means that if it is true, it will take that one. If it is not true, it will go with this one, the separate one.
You need to check that one first.
You need to check, yeah. You need R does not do it. Unlike if you look at the SPSS, it will do this and tell you that when they are equal, that is it. When they are not equal, that is it. But when you are interpreting, you need to check which one you are doing. But in R, you can easily do that. The test is called var dot test. So this is like the F test we used to do in the undergraduate session. So var dot test is what? F test to compare or two variances. So when you test this, so for example, when you test and it is equal, you put equal. When it is not equal, you put also not equal. So that's it with these tests, the T test. And it's time. Is it not 5:30? 2 hours. Oh, you people. You have another class? Hey. Okay, so please, he's not here. Is it Mr. Bondi? Is he here? My people, it's not true. Okay, so let me end here. Okay, so remember that whenever we are doing a hypothesis, there is a confidence level. Okay, so it is not always 95. Okay, if you go to the health people, sometimes they require that if you have 30 Ghanaians, we are 30-something million. So if you leave 5%, that the 5% error, you can make 5. Then, assuming 5% of that's there. So sometimes they said their confidence level so high, 99%, right? So it means that if it's 99, you must change this to what? 0.99. So that's how you do this. Okay, but please let me finish my test before I go. What did we want to test? No, this one, the seat belt. Will causing, yeah. Okay. So how do we do this? Well, it's the will cause test. So if you check here, it says will causing what? Rank some test. If you have done any test of hypothesis, we would have. Yes. So here it will cause the test. So it's the same as the T test, almost the same, right? Okay. But what I don't know now is how to arrange them. So auto BI, let me just try and finish this soon. Okay. So I need to select all the auto BIs with seat belt equal to 1, right? Oh, when you are in a hurry. The seat belt, okay, equal to 1. So, so, okay, so this, if I do it, this is a question mark, right, to check whether the seat belt is equal to 1. So you see, I get true for those that are equal to 1, and those that are not equal to 1, I'll get what? False. Okay. Now, if I pass through to the laws, those that are true will be selected. Those that are not true will not be selected. So if I negate it, it now becomes what? Those who were not wearing seatbelt. Okay. So now this will be seats. Okay. Okay. So let me say seatbelt laws. Will be this. Okay. Then I can copy the same thing and negate it. If you want to negate, it's just you put exclamation sign. No seat belt laws. So here I can do it this way. I can exclamation. This is not equal to. Or I could have just done it. So two ways. Either I do this equal to 2, right? Because that's 2, right? Okay, so that's one way. Let me comment one of them out. Another way is that you say not equal to 1. So when you go home, please check. You can do the 2 and check. Oh, not equal to 1. Okay, so when I do this, I'm going to get... Oh, not equal to 1, rather. Sorry. So not equal to 2 will be the 1. Yeah, good. Okay. So those wearing seatbelt, these are their data. Those not wearing seatbelt, that's their data. Okay. Not wearing seatbelt. Equal to 2. Why am I getting... Okay, so let's see. Auto BI equal to 2. Okay, so there are not many at all. Just a few. Okay. So what do I do now? That 1 will be S, 1 will be what? Y. So from all what we have done, I can copy this and paste over here. Okay. What I'm doing is to replace X with what? Seat belt. Y with what? No seat belt. Is everybody okay? Good. And then alternative. What was our alternative? It should be less, right? Less, okay. So I can delete these ones. Greater and two-sided. Mu is 0. Is it paired? No, so we leave it like that. The rest, they are not really needed. Confidence interval, if you want. Confidence interval is good, so maybe we can say true. Exact, and then exact, I can take it off. Correct is true, I can leave it. These ones, I don't need them, I can take all of them. The confidence interval, do we want 95? It's okay. Then we can leave it like that. Okay, so then we perform this test. So that's the test. Oh, my battery is telling me that it's time. Okay, let me just interpret the results and then I can leave you. Okay, so the data we used was what? Seat belt and what? No seat belt. Okay, our W, which is the workhorse test statistics, is 8,000 so and so. P value is 0.0062. Okay, then we got the confidence interval, that is negative infinity to this. Okay, now I'm going to use each of them to 2 of them. This one, if I want to use it, I have to go to and read the workhorse from the workhorse table. What is the test statistics? Then I compare it with it, just like we were doing here. I gave you T9, so that can be done. If I want to use a p-value, our alpha was what? 0.05, right? Good, okay. So I check, is the p-value less than 0.05? So what do I do? Because you reject if p-value is less than alpha. P-value is less than alpha. Alpha is 5%, 0.05. This one is 0.0. So we reject the null hypothesis. What does that mean? We were testing this one. But of course that was 0. Yes, so it means that. Good. Yeah. Is everybody okay with this? Yeah, that's it. Okay. You can also use the confidence interval. Okay. Remember that the difference between them is 0. If it is 0, then I expect my confidence interval to enclose 0. Is everybody okay with this? If it is 50, I can also send the 50 over there, then I get 0. Or you can then expect that your confidence interval should enclose what? 50, if this is to be true. Okay, so we check. Our own is from negative infinity because it's one-sided test. Negative infinity to... Does it get to 0? No. So it means it doesn't include 0. So what do? you reject the null hypothesis. Is everybody okay with this? Yeah, so that's how you interpret this kind of graph. So when you go home, please check for, you can also check for two-sided. So if I can just take this off and then it becomes two-sided, then you rerun it. If you run it, the results will be different. So the confidence interval will no more be infinity. So you look at it, it's now what? -3 to this. You can interpret this as well. Okay, so the p-value is still small, so what do? You reject. Okay, and then when you come here, the interval doesn't include 0 as well. So what do? You reject. So whichever way you look at it, wearing the seatbelt is better than not wearing. But you see the graph did not give us that. Yeah, so test of, and if you use a t-test, you may reach the conclusion in the other way because normality is not as, normality assumption is not true, and so forth. Okay, so I'll leave the other one to you as an assignment where you check the marital status. So there, you cannot use ANOVA. So what I want you to do is that when you go look at the health files for AOV, so ANOVA, I should type it there. So AOV, that is analysis of variance. Okay, but that is not satisfied, right? So what you need to do is to look for Kruskal.test. So you can check the health files for that. There's actually a video, so I'll send it to you on this. And then you set it. So please, you will die. You won't die now. You will get past 120 and smash the Guinness Book of Record before. Okay. Yeah, but it's important that you understand this kind of hypothesis from practical point of view, not like those days you have to use from them. So, yes, that's it. Any question? Okay, all right. So please do that. I'll send you I'll check and send out the link to the video on this. Please take your time, go through it so that you can check for the marital status. Okay, so you have to check for normality assumption. You have to test for equality of the variances, which is the Bartlett test, before you do the Kruskal-Wallis.